Mhm. Hello everybody, I'm happy to continue our lectures in 2021, new year. And first of all, I have to explain a little bit about point rating system, and maybe I used wrong terminology when I said about written exam. This is not a written exam, better to say written tests. So in fact, firstly we plan to do them continuously during the semester, but somehow it didn't happen, so that is why those tests will be collected in one set, and it will happen on Saturday with your seminar teachers. So that is a part of semester, and in fact this makes the total system closer to what is going on in Russian speaking studies here. So usually students have not only written exam but also a kind of written test which is very similar of what is supposed to be on Saturday. That is what you will get on Saturday. In fact, problems will be created by seminar teachers, and so you may ask them about more detailed content of that test or exam, maybe. If we'll use the word which I used. But once again, that is not a part of the system of exams. So your exams will start in 2 weeks. So next week is for, so in fact, as far as I remember, it will start next week, right? The week of exams. So Saturday is not yet day of official exams. Okay, concerning the content of the final exam, questions for the final I'll present in next future, I hope. And of course they will include all questions of our midterm exam. That is standard for our system. So midterm exam was not a part of exam, it was for intermediate control only, and the final exam is to control the content of everything. Okay, so I wonder if there are questions about what I said about system of exams. And it seems no questions. Okay. So, today is section 28.1 and lecture 28, and it is called, how it is called, conditions for a local extrema of a function. So we'll start with first proposition, which is called necessary conditions for a local extrema. In fact, we need not to prove anything, so just this is an easy consequence of Fermat theorem. So we know that if a differentiable function has a local extrema, then derivative is 0. Hence, immediate consequence is if f is defined in a neighborhood of x0 and x0 is a point of a local extremum for f, then either f is differentiable at x0 and f prime at x0 is 0, or f is not differentiable as x0. So that is an immediate consequence of the Fermat theorem. Okay, first question about. Yes, the question if the oral examination is similar to our midterm exam. Yes, it's indeed very similar, and in fact one of main goals of our midterm exam was to create some kind of knowledge of students about the process. That is okay. So now, as I said, the proof is not necessary, since the proposition is an immediate consequence of Fermat theorem. So if f is differentiable and it has an extremum at x0, then derivative is 0. That is Fermat theorem. So other possibility is that f is not differentiable. That's all. Okay, example. f of x equals to x cubed. Okay, example 1. F of x is x cubed. So x naught equals to 0 is not a point of extremum. Why? Because what happens with our function near the point? So if we look at the derivative, f prime of x equals to 3x squared, then this is positive for all x not equals to 0. So it means that it follows from the proposition from the last section about conditions of monotonicity that f of x is increasing on R, and in fact strictly increasing Why strictly increasing? It is obvious for x not equals to 0, so for x positive and negative, but it is valid for all x's as well, as it can be seen from, so look, if x1 less x2 and all of them are positive, then f of x1 less than f of x2 by conditions of monotonicity, derivative is strictly positive. Analogously, we can proceed for negative f of x1 less than f of x2. And if x1 equals to 0, then f of x1 is 0 and it is strictly less than f of x2. And analogously, we can proceed with x2 equals to 0. And after that, if x1 less 0 less than x2, then we deduce f of x1 less 0 less f of x2, and it means that we have strictly increasing function everywhere. And also it means that x not equals to 0 is not a point of a local extremum, but f prime at x naught equals to 0. So this example shows that our condition, in fact here we refer to the first part, is only necessary, it is not sufficient. So this condition, f is differentiable and f prime equals to 0, is satisfied for that function. Nevertheless, the point x naught equals to 0 is not a point of a local extremum. That is, by the way, this is also an example for conditions of monotonicity. So you see that we have strictly increasing function despite of the existence of a point where derivative equals to 0. So the conditions for strictly increasing functions, namely that the derivative is positive are sufficient but not necessary. So if derivative is positive, then the function is strictly increasing, but if the function is strictly increasing, the derivative need not to be positive everywhere, as this example shows. Okay. Analogously, maybe I'll give another example when it works. If we consider f of x equals to x squared, then x naught equals to 0 is a point of a local minimum, and it satisfies that condition, right? So here necessary condition works. Third example, f of x equals to modulo x. Here x naught equals to 0 is a point of a local minimum, and here the second part works, so the function is not differentiable. And fourth example, f of x equals to, as it is given in your lecture notes, x positive to x negative. What's about 0? Nothing about 0. Okay, but it's better, let me add something to include 0. So otherwise, yeah, f should be defined in the neighborhood, right? So here x naught equals to 0 is not a point of a local extremum, although the function is not differentiable at x naught. So this shows once again that the last condition also is not sufficient. It is only necessary for a local extremum. Okay. Maybe a local extremum, of course, a local extremum. Why I used extremum? English should be correct. Yeah. Okay. Okay. That is everything what I wanted to give you concerning this necessary condition. Now we want to wait a minute, there is one more. Okay. And that is proposition 2. Proposition 2. Now we want to clarify sufficient conditions. So sufficient conditions for a local extremum. But here I should indicate in terms of the first derivative. if f is continuous at x naught, differentiable in a deleted neighborhood of x naught, and they exist b minus of x naught left hand side, left neighborhood, the set of x such that x naught minus delta less than x naught, and b plus at x naught x such that x naught less than x naught plus delta, such that now I should write 4 different conditions, 4 different cases. So let's start with the first. So in fact, we are talking about all possible signs of derivative in those one-sided neighborhoods. So for all x in b minus of x naught, f prime of x less than 0, and for all x in b plus of x naught, f prime of x less than 0, then f has no extremum at x naught. Analogously, for all x in b minus f prime at x greater than 0, and for all x in b plus f prime of x greater than 0, then f has no extremum at x naught. Third, for all x in b minus of x naught, f prime of x less than 0, and for all x in b plus at x naught, f prime of x is greater than 0, then f has a local minimum at x naught. And last, fourth, for all x in b minus of x naught, f prime at x greater than 0, and for all x in b minus f prime at x is less than 0, then f has a local maximum at x naught. Okay. Shortly, and in fact not completely correctly, usually this is expressed by words here: derivative changes sign in passing x naught. But this is not completely correct. Why? So before the proof, let me give an example which shows why this is not true in general. So example: we consider the function of this 2x squared plus x squared sine 1 over x if x not equals to 0, and 0 if x equals to 0. So how the graph of that function looks like? You see, if sine is minus 1, we have x squared. That is, let me draw the picture. 1, 2, 3, 4. So that is y equals to x squared. Right? Minus 2, minus 1. And if sine equals to plus 1, then we have 3x squared. It gives something like that. That is y equals to 3x squared. 3x squared. And concerning our function, it oscillates somehow between those two parabolas, and symmetrically symmetrically, but not, we have no, the function is not even, in fact. Analogously, better to say, not symmetrically. Analogously in the negative, right? Or something like that. So you see that, in fact, if we'll compute the derivative, f prime for x not equals to 0, that is 4x plus 2x sine 1 over x minus cosine 1 over x if x not equals to 0, and the derivative at 0 can be computed by definition. That is 2x plus x sine 1 over x. Here we have limit is 0. Here we have a product of infinitely small function times a bounded. So we have 0 in any cases. And yeah, so the derivative is well defined, and we see that when x approaches to 0, the sign of derivative is completely determined by the sign of cosine. So if cosine is positive, then derivative is negative, and vice versa. And cosine changes sign infinitely many times when we approach to 0. Hence, the direction of monotonicity of our function f of x changes infinitely many times when we approach to 0. So when you say derivative changes sign in passing x naught, look here, derivative changes sign, but it does it infinitely many times, and that it's definitely is different from what is written here. And look, here, of course, the function has a local extremum, right? So it's okay, but we can change it slightly. So look, that is 1, example 2. So let me consider, let's say f of x equals to 2x cubed plus x cubed times sine 1 over x squared, let's say. So if x not equals to 0, and 0 if x equals to 0. So then what will happen? We have analogous structure of the function. So y equals to x cubed and y equals to minus x cubed. 3x cubed, and the graph of our function oscillates infinitely many times between those two cubic parabolas. Analogously, it will from that side. Okay, somehow like that, right? So you see, here once again, derivative changes sign in passing x naught, and in fact it changes sign infinitely many times, because here the derivative is equal to, if we will compute, so 6x squared plus 3x squared sine 1 over x squared, and minus, so what do we have here, minus 2 derivative of 1 over x squared minus 2 over x cubed, so minus 2 cosine 1 over x squared. If x not equals to 0, so you see cosine changes infinitely many times, and it means that the sign of derivative changes infinitely many times when x approaches to 0. So if you say derivative changes sign in passing x naught, you can apply it to that function as well, but the function has no extremum at 0. That shows those words, using of those words is not correct. That is precise. Okay, now proof. 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 Okay, we'll start with the first. So if derivative is negative for left neighborhood, it means that the function f is decreasing on x naught minus delta x naught, and analogously it is decreasing also on x naught minus delta x naught. Then, according to properties of monotone functions, there exists a limit as x tends to x naught minus f of x. This limit exists. And because of continuity, in fact, it is equal to f of 0. And we also deduce that for all x in B minus of x naught, we have f of x greater or equal than f of 0. Because f is decreasing. Analogously, by general properties of monotonic functions, there exists a limit as x tends to x naught plus, and once again, because of continuity, it should be equal to f at 0, and for all x in B plus, we have f of x less or equal than f of 0. And you see, it means that we have no extremum, since there is no possibility to choose a neighborhood where we have just one of those signs. We have only opposite signs. Yeah, and in fact, yeah, we guarantee here, because of strict inequality, I may prove this is strict inequality. We have strict inequalities here everywhere. That is, it shows that no extremum. Yeah. Okay. Analogously, we can consider the second case. Now, let's look at the third. So, quite analogously, we have the behavior. F is decreasing on x naught minus delta x naught, is increasing on x naught, oh sorry, here I should write x naught plus delta, of course. Yeah. X naught plus delta, and yeah, everything what we should change are signs here. So for all x in B minus x naught, we have f of x greater f of 0. It's the same because we have decreasing, and for all x in B plus, f of x is now greater than f of naught, and those two inequalities show that in fact we have local minimum. And fourth condition, fourth case, is checked unalteredly. Okay, let's have a break. Okay, let's continue, and thanks a lot for your question. Indeed, I made a misprint. There's the reason. So, of course, everywhere instead of 0 should be x naught. So please correct it. Yeah. Okay. Also, I would observe that, in fact, what we proved just now shows that we can assert even more, namely, f has a strict local minimum, strict local maximum. In both cases, we can say about strict local maximum or minimum. Also, of course, yeah. But, okay, let me stop here. Concerning this proposition 2, let's stop. Okay, now this was about sufficient conditions in terms of the first derivative. Now what's about other sufficient conditions in terms of higher derivatives? Let us formulate. So proposition 3. Sufficient conditions for a local extremum in terms of higher derivatives. If f has okay, let me write just by notation. Nth derivative at x naught and f prime at x naught equals to second derivative and so on up to the derivative of order n minus 1 equals to 0, nth derivative is not equals to 0, then for n odd, f has no extremum at x naught. For an even, f has a local, again in fact strict, but I'll not write it explicitly, a local maximum at x naught for f nth derivative negative and f, okay, let me use if f has a local minimum at x naught if f nth at x naught is positive. So, in terms of the first derivative, we could conclude the existence of a local extremum if the signs of the first derivative are different from different sides of x naught. And here the situation is different, and for n even we can conclude about local maximum minimum just from the sign of the derivative, the related derivative. Okay, proof. Let us use Taylor formula with remainder in Peano's form. So, in general, let me recall that if f has nth derivative at x naught, then we can write, in general, this looks like kth derivative at x naught over k factorial times x minus x naught power k plus little o of x minus x naught power n as x tends to x naught. That is the formula. From our conditions, those conditions, what we deduce? In this sum, all terms except of the very first and the very last are zeros. The last is certainly not 0. The first may be 0, maybe not, doesn't matter. So what remains if, so by the supposition we can write f of x equals to f of x naught plus nth derivative at x naught over n factorial times x minus x naught power n plus little o of x minus x naught power n as x tends to x naught. So, firstly, consider n is odd. Let me rewrite f of x minus f of x naught equals 2 as derivative at x naught n factorial. And I'll write like that. Little o of 1 times x minus x naught power n. That is not 0. And what means little o of 1? That is something what tends to 0 as x tends to x naught. So this is infinitely small function. And it means that for there exists delta greater than 0, such that for all x which satisfy the inequality x minus x naught less than delta, the sign of this expression is completely determined by the sign of nth derivative. So signum of sign of this expression equals to the sign of nth derivative. Now, if x is between x0 and x0 plus delta, then what can we deduce? Signum of the difference f of x minus f of x0. Here we have n is odd, recall. X is minus x0 is positive, so this is positive. This term has the same sign as this one, so signum is equal to signum of nth derivative at x0. And if x0 minus delta less x less than x0, then for n odd, this is negative. So this will be negative, and it means the sign will be opposite to the sign of nth derivative. And what is more important for us, that the difference between f of x and f of x0 has opposite signs from different sides of x0. And it shows that f has no extremum at x0. So the first case is considered. Now what happens, let's say n is even, I'm sorry. What should be changed then? N is even. In fact, the first part is completely the same. First two lines of the proof need not to be changed. But now look what happens. X minus x0 power n, when n is even, is positive in both cases. So it means that for both, so if x minus x0 in modulus is between 0 and delta, then in both cases we have the same sign. Equals to the sign of nth derivative. So it means if this derivative is negative, then f of x less than f of x0, and we have local maximum. And if nth derivative is positive, then this is positive as well, so f of x greater than f of x0. And it means f has a local minimum at x0. And the proof is completed. Okay. Now, example. Consider the function f of x equals to sine x. So by necessary condition, because of differentiability, our function is differentiable everywhere. Hence, it can have a local extremum only when the derivative, which is just cosine x, is 0. Cosine x equals to 0 is equivalent to x equals pi over 2 plus pi k, where k is an integer. So these are points where sine can have an extremum. Now we can investigate what is about extrema at those points indeed. So if you look at second derivative, that is minus sine x, and you see that everywhere at those points that is minus sine pi over 2 plus pi k. So if k equals to 0, that is minus 1, k equals to 1, plus 1, and so on. So we have minus 1 power k plus 1. So k is even, the sign will be minus, k is odd, the sign will be plus. So you see, it is never 0, and it means that we can apply our proposition with n equals to 2, n equals to 2. So n is even, and it means that our function has local extrema at those points, at every of those points, and for k equals to 2m, where m is integer, x equals to pi over 2 plus 2 pi m is a point of, so for even we have minus, and it means that we have local maximum, and if k equals to 2m plus 1, m integer, then x equals to, let's say, 3 pi over 2 plus 2 pi m is a point of local minimum. That is how the proposition works. Okay. Now I think it's better to start a new section. Okay. New section, classical inequalities, 28.2, classical inequalities. And I'll start with lemma. Lemma is given as example in your lecture notes. In fact, example for former section. So, not show, because this is lemma. For x positive, we have two inequalities: x power alpha minus alpha x plus alpha minus 1. is non-positive when alpha between 0 and 1, and x power alpha minus alpha x plus alpha minus 1 is non-negative when alpha less than 0 or alpha greater than 1. So, proof of that lemma. So we put f of x by definition as this function. Now take a derivative f prime, that is alpha x power alpha minus 1 minus alpha. So I may rewrite alpha times minus 1. And now what happens with this? So f prime of x equals to 0 if and only if x power alpha minus 1 equals to 1 or x equals to 1. Because the case alpha equals to 1 is excluded. Alpha not equals to 1. Right? So, then, what's about sign of f prime? It depends on alpha, of course, right? So, if alpha is greater than 1, then what happens? Here the exponent is positive. It means x power alpha minus 1 is an increasing function. So for x greater than 1, then f prime of x is positive, and for x between 0 and 1, f prime of x is negative. So it means that what we have? We have that x equals to 1 is a point of local maximum, is a point of a local maximum, and in fact, because of those directions of monotonicity, we can conclude this is not a local but global. So a point of a maximum. So is the maximum point, better to say, right? The maximum point. All right. So and what is the maximum? F of 1 equals to, what is f of 1? 1 minus alpha plus alpha minus 1 is 0. So we have, in this case, if alpha greater than 1, then f of x is less or equal than 0, always. What? Oh, sorry. Firstly, I wrote right hand side positive, minimum. point. So f of x greater or equal to 0, and it means that we proved this case, right? Other cases are considered analogously. So you see, let's say, okay, 0 less alpha less than 1. Here we have negative. It means the function x power alpha minus 1 is decreasing, so we have x greater than 1, then f prime of x less than 0, and x between 0 and 1, f prime of x greater than 0, so hence x equals to 1 is the maximum point now, and what it gives, that f of x is less or equal than 0, and that is precisely what is given here, right? And the last case, alpha less than 0. Here once again we have negative, so it's still same distribution of signs but only for the brackets. And if we multiply by alpha, which is negative, then we should change signs. So x greater than 1, f prime is positive, 0, f prime is negative, and once again same as for alpha greater than 1. So last case is considered and lemma is proved. Now we'll use this lemma for Young's inequalities. Jung. I'm not sure in pronunciation. Usually in Russian we say Jung. So Jung's inequalities. Again, let A positive be positive, PQ are such that P not equals to 0, 1, Q not equals to 0, 1 as well, 1 over P plus 1 over Q equals to 1. Okay, yeah. Then this is wrong. Suppose, right? Suppose PQ are such that then A power 1 over P B times 1 over Q less or equal 1 over P A plus 1 over Q B for P greater than 1, and same product is greater or equal this expression for P less than 1. Okay, Proof. Proofs. We'll refer to lemma, so put x equals to a over b and alpha this is alpha. What is alpha? 1 over p, yeah, 1 over p. 1 over p. So, yeah. It means that that is for p greater than 1, right? Then we have 0 less alpha less than 1, so it means we can use the first line, so let me rewrite it. A over b power 1 over p minus 1 over p a over b plus 1 over p minus 1 less or equal than 0, right? Now, what we have here, that is 1 over minus 1 over q, because of the definition, right? 1 over p minus 1 is minus 1 over q. Okay, so let's multiply by b. So multiply by b, right? What we'll obtain then? A power 1 over p times b power 1 minus 1 over p. Multiply by b, we had this one. That is less or equal than, so everything else I'll put to the right hand side, 1 over p a plus 1 over q b. And you see, this is precisely what we wanted. So that is the proof, right? And yeah, for p less than 1, the proof is quite analogous. Here, alpha equals to 1 over p will be, okay, here we have two cases, right? If alpha will be greater than 1 for p positive between 0 and 1, and alpha will be less than 0 for p less than 0, right? And everything else is the same, right? So, but we have opposite inequality here and proceed in the same way. And the proof of Young's inequalities is completed. Okay, now, yeah, I think I'll be 5 minutes. Oof. Not good. Holder inequality. Okay, I can classical inequalities. Maybe let me change the title to Young's inequalities. Yeah. And yeah. So maybe I'll finish the proof in more details then, right? So for p less than 1, we have alpha 1 over p, alpha greater to 1 for this and alpha less than 0 for that. And now the second inequality gives us a over b power 1 over p minus 1 over p a plus a over b, sorry, a over b plus 1 over p minus 1 greater or equal than 0, right? Because here we have alpha less than 0 or alpha greater than 1. Now we multiply by b. Once again, we can do it because of positivity of b, right? So what it gives, a power 1 over p times b 1 minus 1 over p greater or equal, we put to the right hand side. Yeah, so that is precisely the same as before up to the sign of the inequality, right? And 1 minus 1 over p is once again equals to 1 over q. Yeah. So indeed it works even for p negative. Yeah, of course, the case when p are negative is not usual, but it is correct. It is correct. Yeah, yeah, it is correct. Yeah. I guess maybe you know very well particular cases. Look, when p equals q equals to 2, then the first, we have first case, and the inequality will be a b square root less or equal a plus b over 2. This is so-called the inequality between geometric mean and arithmetic mean. That is very famous inequality for all a and b positive, right? Yeah. Here a, b are positive. And by the way, maybe I forget to say when we have equality sign. Yes, when we have equality sign. Equality sign only for a equals to b. Why? Because here we have equality sign only for x equals to 0. So equality sign for x equals to 0 only. That is an improvement, in fact, right? That is an improvement. And this gives the following consequence. Yeah, that's quite important. So once again, here we have equality only for a equals to b. That is also quite important. Okay, let's stop here. Thanks for a good question. Okay, bye.